Now in the next section, we will talk about lossy source coding, or it's also called rate distortion. Why will we do this? So if we do digital communication, then we have to convert source signals into bits. And normally a source signal is in waveform, and we have to digitalize this waveform. It's sampled in time and quantized in value. You know this from signaling theory. And there you had the sampling theorem, and this guarantees if the waveform energy is located in a limited amount of bandwidth, then we can sample the signal without losing information about the signal. However, we lose some information by quantizing analog sampled value to bits. And the rate distortion theory characterizes the limits of quantization. Somehow quantization is a process of representing finite analog signals by finite numbers of bits. From this perspective, quantization is the same as lossy source coding or lossy compression. So remarkable rate reduction is achieved by coding over long sequences of bits. So we will now allow some distance between the original signal and the received signal. And you will see how much we can compress the data if we allow such kind of rate distortion. Let's go into more little bit details. So we will look at such a model here. We have a source again. It puts out some sequence xn, and the source encoder again maps it to some message w. And the decoder have to encode now by a function x hat n of w the sequence. But now we allow some rate distortion. It's this d here. That means we allow some distance between the original sequence xn and the decoded sequence x hat of n. So the smallest required rate decreases with the increasing distortion. And this suggested shapes such as those shown below. So if you look here, of course, if I increase the distance, then of course the rate can be smaller. So again, we want to do some kind of data compression. So we want to make the rate as small as possible. Of course, if you go to the right and make d bigger, then this function should decrease. I think that's obviously. So let's define it in more details. Again, a discrete minimal source with alphabet x emits a sequence xn that is passed to the source encoder. The encoder quantizes xn into 2 to the nr sequences x hat n of w and sends the index w to the decoder. The decoder puts out now the reconstruction x hat n of w of xn. And the letters x hat I take on values in the alphabet x hat. Normally, one assumes that it's the same alphabet, that x hat is equal to x. And our goal is to ensure that a non-negative and real value distortion function, here called dn of xn and x hat n, is within some specified value d. We will look at the less restrictive version of this problem. We want that the average distortion is at most d. So some example of distortion functions. So a commonly used distortion function is, of course, the Hamming distance. Then we just count the number of different symbols here. So this gives 1 only if the symbol at the ith position of x is different of the symbol at the ith position of x hat. now we count the number of different symbols in the sequences, and then we take the average. Another commonly used function is the Euclidean distance or straight arrow distance. Then we just take xi minus x hat I and square it and take again the average. And if you see, that's what we always assume, that we consider sequences of distortion function of this form that we average over the single symbols. That's usual. Now the rate distortion problem is find a set of pairs D and R such that one can approach with a source encoder for sufficiently large n. So this, when we look for the smallest rate as a function of the distortion D, then we call this the rate distortion function. So that we will do. So we will look for the smallest r. But we can also, there's also a theory which does the other way around. So we give the r, and then we look for the smallest d, and this is called the distortion rate function. But we will only consider the rate distortion function. So the idea now, how we do this, is we construct a random code books for the channel coding problem. That means we begin by choosing a channel x hat x, so, and compute the marginal distribution of it as of the joint distribution x hat. So the idea is really to have an auxiliary channel, some kind of channel, which we use to, if we receive some sequence with some letter of a sequence with some probability, we map it to another letter of the sequence. That's what we will do. Of course, that's possible. And now we make a code construction. The code construction, we just take this marginal distribution, and we will generate two NR code works, x hat n of w. Just randomly, we do it letter-wise. You can think of it on the next page. I will show you how it is. It just, we have 2 to the NR sequences and of length n, and each letter is independently constructed randomly. So we should, here it's written down by choosing each of the n times 2nr symbols independently using this marginal distribution px hat. And we choose a default code work x hat to nr plus 1, which is equal a, for all I where a is the letter such that the expected value is d max. So we always assume that the expected value is bounded. So the overall rate, therefore, is reduced by the factor 2nr over 2nr plus 1, because we have one default code word here. But in principle, for large n, this goes to 1, and it gives the same rate. So now the encoder, he gets by the source an xn, and now he chooses a w, one of the messages that minimizes the rate distortion function here. So we have this list, this code words. I will explain it on the next slide again. The list of code words, and we receive one xn by the source, and this, the encoder just compare it, which gives the lowest distortion rate. And he chooses perhaps there are more than one sequence which gives the lowest rate. But then we make some appointment with the decoder that we always choose the first one. And then he sent W to the decoder. And the decoder, of course, he also has the same codebook. He can reconstruct x hat n of W. Let's look at this codebook. That's the way the codebook is constructed. So we randomly choose this letter, this letter, this letter, and so on. So we construct these letters here randomly and independent. And then we have a codebook list. So x hat n of 1 is equal to this sequence, x hat n of 2 is equal to this sequence, and x hat n of 2nr is equal to this sequence. And now if you receive a sequence, then we just compare it and search. So we receive your sequence xn and compare it here with our codebook and choose that sequence, which is the nearest one when the rate distortion is as small as possible. And then we look for this W. Let's assume it's for example, the second sequence here is the one who produced the lowest distance. Then we send a 2 to the decoder. And the decoder, he also has this list, can of course reconstruct x hat n of 2, and then we can calculate the rate distortion distance.